Today we're going to talk about mole conversions. Mole conversions are just conversions using the mole to go between different units. So similarly as earlier we used dimensional analysis in order to go from, say, milliliters to liters or from centimeters to inches, we're going to do very similar problems today, except we're going to use the mole to convert between different units. So to begin with, let's talk about solutions. One solution that we're looking at here, where this giant cup that this guy is holding down here, is of coffee. So let me ask you the question. If you were to wake up in the morning and you're used to drinking espresso, what if somebody switched you out and gave you decaf? Would you be angry? Would you notice? I think you would notice. There's this thing called addiction that seems to happen over time. But why would you notice? What is different in a regular cup of coffee as compared to decaf or as compared to espresso? It's the caffeine content that you'd be addicted to. So if you drastically change the caffeine content in your morning cup that gets you going, you can have drastic differences in not only your mood, but other physiological effects. So when you're talking about the actual differences in decaf versus regular versus espresso, what you're looking at is the different amounts of caffeine in water, okay, which is the sample, your solution, right? So in this example, we've talked about solutes and solvents. Your solvent, what is that? Water. And your solute, that in this case is your caffeine, okay? That's one of the small molecules that comes through the filter as you put the hot water into the coffee filter that has all the beans in it, all that stuff, but caffeine comes through. In decaf coffee, approximately 2 milligrams will come through per 8 ounces of water. And regular, you'll have 95 milligrams per 8 ounce of water. So you notice with those two, your regular has, what is that? It looks like 47, something like that, times more caffeine than decaf does, so a lot higher concentration. But when you switch to espresso then, how come it's in between? You've got 64 milligrams. That's in the middle of 2 and 95. So how come we say espresso, it has a lot more caffeine in it? Well, if you do the math, notice here we've got per 1 ounce. For decaf and regular, I reported these units as per 8 ounces. So if you were to convert 64 milligrams per 1 ounce into per 8 ounces, now you can see the huge difference here. 512 milligrams of caffeine per every 8 ounces. So if you only drink 1 ounce of it, it's about equal to a cup of coffee. But if you drink a whole cup of espresso, you're drinking 5 times the amount somebody would have consumed if it would have been a regular cup of coffee. So with this, when we're looking at here with solutions, solutions are a way of expressing what's called concentration. So here you have your solute, which was our caffeine. And you have your solvent, or really in this case it's really going to be your solution because it's the total volume that's in your cup, not just the total volume the water takes up. So that's going to be your coffee, which is mainly composed of water, which is your solvent. So when you're expressing concentrations, it's a way of letting us compare between things. Because if you were to just say, well, decaf, regular, and espresso, if you didn't have the language that allowed you to identify how much caffeine was in your pot, then you wouldn't be able to compare between them. You could be able to tell physiologically, but what if there were no standards in the world? Nothing that said, oh, if you have approximately 2 milligrams per 8 ounces, that's classified as decaf. What if I classified my decaf as 2 mgs per 8 ounces, and somebody else classified their decaf as 512 milligrams per 8 ounces? We wouldn't have a standard to compare, and so you may wake up one morning really hyper, and another morning you may still be a little bit tired. Okay? So solutions just simply allow us, concentrations just really allow us to explain what's happening in a solution. To go a little bit further on this concept then, we can look at examples that allow us to determine what's called molarity. And molarity is really going to be the emphasis of today's lecture. But in order to understand molarity, we have to look at what's called molecular weight, and we have to do these molar conversions so that we can express our concentration and molarity. So molarity is just a unit that expresses concentration. So we're going to use caffeine as an example today to determine all of these things. Molecular weight, which another way of saying molecular weight is molar mass. We're going to use it to determine molarity, and we're also going to look at it to see how many caffeine molecules would exist in 1 ounce of espresso. So, first of all, molecular weight. If you remember, we've been talking about this whole time about how the atomic number, our Z number, which is designated here for carbon as being 6, that is our number of protons. We have then our chemical symbol C for carbon. What is this number down here? What does that tell you? That's right, that tells us the mass of carbon. Okay. What type of mass, though? Well, for carbon, it's 12.011 grams per mole is what that mass is. So per mole, what that means, if we have 1 mole of carbon, we can expect the carbon to weigh 12.01 grams. So if we have, for instance, in caffeine, if we have 8 moles of carbon, then how much would we expect the weight to come from carbon? So if we have 8 moles, let's multiply this by 8 moles. Okay, I'm using MOL as an abbreviation, short for mole. If we go 12.011 times 8 moles, we pull out our calculator, we type that in, 12.011 times 8. That gives us a total of 96.088 grams of carbon. So if we have 1 mole of this whole substance, that means we have 8 moles of carbon, right? Or another way of thinking about it is in molecules. You can use the terms molecule, moles a little interchangeably at this point, but they really matter later on. So if you have 1 molecule, for instance, of our caffeine, that has 8 carbon atoms. Another way of saying that is 1 mole of caffeine molecules would give you 8 moles of carbon atoms. Either one is technically a correct way of looking at this sample. So if, for instance, we have 1 mole of caffeine molecules, then that means 96.08 grams will come from carbon. If we do the same thing for hydrogen, hydrogen weighs 1.0079 grams per mole. We come back up to our molecular formula, and we see that there are 10 hydrogen atoms in every mole of the molecule. So we multiply this by 10 moles. So that gives us a total of 10.079 grams are going to come from hydrogen. Next we do nitrogen. 14.007 grams for every mole of nitrogen, times there are 4 of them in every molecule or in every mole. So we've got times 4. And if you want to put all these over 1, that's perfectly acceptable. Or you can just leave them and know that they're on top. So 4 times 14.007 gives us 56.028 grams coming from nitrogen. Then with oxygen, we've got 15.999 grams per mole. And with oxygen, we come right back up to our molecular formula, and we see that there are 2 moles. So 15.999 times 2 gives a total of 31.998 grams coming from oxygen. So whenever you're trying to express what the molecular weight is of the whole caffeine molecule, why I broke this down for you is because that can allow us to say, oh, if you have 8 moles of carbon, then it should weigh 96.088 grams. Caffeine also has 10 moles of hydrogen, 4 moles of nitrogen, and 2 moles of oxygen. So if we add up all of these numbers, so all of these numbers right here, if we add all of these up, then what we're doing is we're figuring out what the mass is of 8 moles of carbon plus 10 moles of hydrogen plus 4 moles of nitrogen plus 2 moles of oxygen, because that will give us the mass of 1 mole of caffeine molecules. So whenever you ask what is the molecular weight of a substance, you have to first figure out the structure of that substance. Then you look up the individual atomic masses. Those atomic masses then need to be multiplied by the number of moles of the atom in the compound, and then you add them all up. So let's add them all up for this compound. So we got 31.998 plus 56.028 plus 10.079 plus 96.088. If I did that correctly, it should be 194.193, and that's grams of caffeine. Per how much though? Per 1 mole. So we have, and you can't really see my decimal, let me make that a little more obvious, 194.193 grams of caffeine per mole. Go ahead and write this down, make sure you remember it, because we're going to be utilizing that a lot today. So this answers our question of, if you have 1 mole of caffeine, how much does it weigh? It weighs 194.93 grams. If I were to ask you, how much does 1 mole of carbon weigh? You come back to the periodic table, it weighs 12.011 grams. So molecular weight is the way of comparing the mass of substances based on using the mole as our thing to compare to. All right, so let's figure out what the molarity then is. So the question is, what is the molarity of caffeine in a cup of espresso? Down here at the bottom, I've written a couple of equations that will help us out. So first of all, we already talked about, and I wrote this equation wrong. So concentration is the amount of solute per amount of solution, and molarity is the number of moles of your solute per liter of solution. So any time that you know you're talking about molarity, know you're talking about concentration. And because of that, solute is on top and solution is on bottom. Additionally, we always have to represent moles and solute in terms of moles. We can't represent them in terms of molecules. We can't represent them in terms of grams. You always have to have moles of solute if you're talking about molarity. And you always have to have liters of solution if you're talking about molarity. So another way to represent molarity is molarity equals moles per liter. Those are the units you'll end up with at the end of any concentration. So it asks you what the molarity or what the concentration of caffeine in a cup of espresso is. Your answer should have the final units of moles per liter, which is the same thing as saying big M. So you can replace, anytime you see moles per liter, you can replace it with a big M. Or anytime you see a big M, you can replace it with moles per liter. Okay? Additionally, I have in here, 1 ounce equals 29.57 milliliters. Why did I want to give you that? Okay. Well, if we come back up here, we've got ounces. So we need to have something that allows us to convert to liters, because what we want to end up with in the end is liters. And additionally, here is our molecular weight of caffeine from the previous page. I just rounded it down to just 2 decimal points. So let's start this problem. Remember when we were doing dimensional analysis? Basically, anything that could be in parentheses is always equal to 1. So meaning 1 ounce equals 29.57 milliliters. They're equal. So they're a conversion factor because they're equal to 1. So even as we're talking about moles and grams and molecules, you still can only put in parentheses conversion factors. So let's give this a try. Let's start out with 64 milligrams per 1 ounce. And milligrams of what? In this case, we're talking about caffeine. and ounces of what? And that's solution, which I'm going to abbreviate with SOL with an N on top. So we're starting out with that, and we want to end up at the very end with molarity. So let's figure out how we're going to get rid of milligrams and how we're going to get rid of ounces. Milligrams need to be turned into moles. Ounces needs to be turned into liters. But notice, regardless, on the top you have mass of a solute, on the bottom you have volume of a solution. Ounces is a volume, so is liters. So we can make the conversions by simply converting one unit into another. So to start out with, let's look at the top part of this equation first. Right now we've got 64 milligrams of caffeine. We need to get that into molarity. So first off, let's convert from milligrams to grams. You might say, why would you want to do that? Okay. Well, anytime we were looking at the molecular formulas on the previous page, notice, what were my units? We've got grams per mole. Okay. So in order to convert between grams and moles, to go back and forth, we have to make sure we already have it in grams and not in milligrams. So how do we convert from milligrams to grams? If you remember from our previous chapter, you have 1,000 milligrams in any 1 gram. You can also think about it as 1,000 millimeters, if you can picture those on your ruler, in any meter, if that helps you remember this conversion factor. Okay? I'm going to put a big C for caffeine and a big C for caffeine, just so we don't lose our units there. So now on top we have 1 gram of caffeine. All right, so now we can go somewhere with it. If we remember on the previous page, at the very end, we wrote 194.193 grams of caffeine for every mole. So now we can use that as a new conversion factor. So by coming up with all of these molecular weights, it allows us to introduce a new conversion factor into the mix. So our big question is, we've got 194.19 grams per mole. Which needs to be on the bottom? We can either put grams on the bottom or moles on the bottom. We're trying to cancel grams, so we should put grams on the bottom. Notice that this can be written as 194.19 grams over 1 mole. It can also be written as 1 mole over 194.19 grams. Or for short, it can also be written as 194.19 grams per mole. All of these say the same thing, and each one is equal to 1. So you can use any of these options whenever you're trying to figure out your answer. Let me erase this, and let's go ahead and finish this problem out. Takes a little bit to erase on this board. So we have grams on top of caffeine, and we want to turn it into moles. So if we have 194.19 grams of caffeine per 1 mole of caffeine. Let's check our units and see if they cancel out. We're trying to only work on the top part right now. So we've got milligrams on top, and they cancel with milligrams on bottom. We have grams on top, they cancel with grams on bottom, which leaves us with moles of caffeine, which is what we wanted for our final answer. So let's type that all into our calculator. 64 divided by 1,000, divided by 194.19, enter. That gives us 3.2957 times 10 to the minus 4, and that is moles of caffeine per 1 ounce of solution. Notice you don't round right now. You don't pay attention to your sig figs until the very end of the problem. So keep everything in your calculator and don't round it until the end. Let's come back down to this next line. So I'm going to rewrite what we just have up above. So we have the top part of our equation good, but we don't have the bottom part of our thing working out yet. We have it in ounces. So in order to get rid of our, we need to convert it to liters. We don't have a conversion that's to liters, but we do have one that converts us to milliliters. So for every 1 ounce, we have 29.57 milliliters. And notice this is for our solution, and this is also for our solution. Then we're not there yet. We need to go from milliliters to liters. So remember, 1,000 milliliters for every 1 liter of solution. Let's do the math. Let's divide our 3.2957 times 10 to the minus 4 by 29.57, and then multiply it by 1,000. And we get a molarity of 0.011. And let's do 200. Let's go ahead and do 2 sig figs. We only have 1 sig in our fig in our 1 ounce, but in a real problem, we'll probably have more sig figs than that. So, well, we'll just go and round it to the one that's in the problem. So let's do 1 ounce. 0.1 molar solution. So we've got 0.1 molar of caffeine in our solution. So whenever you are asked the question, what is the molarity of, it can be any solute in any solution, you first have to look and see what you're given. So in this case, we are given 64 milligrams. We needed to convert that to moles. Then we also have for our solution, it was in ounces. We needed to get that in liters. So notice, whoopsie, did I do that wrong? Yep, well no, we did that right. Sorry, I was just getting confusing myself. I wanted to go back and double check the units. I forgot to explain that we're canceling stuff out. So we've got ounces, ounces, milliliters, milliliters. We're left with liters on bottom. So if you notice, we've got moles on top, liters on bottom, and that's what gives us our big M. I didn't mean to skip that step for you. So that was our whole point, is we're trying to get the top into moles, we're trying to get the bottom into liters, and we cancel them out just using conversion factors. So molecular weight, think about molecular weight as a conversion factor. You can put the grams on top or you can put the grams on bottom. It doesn't matter, but it does matter when you've got a problem, because you want to make it so the units cancel out, leaving you with moles on top. Okay? So whenever I said, what is the molarity of a cup of caffeine and a cup of other caffeine and a cup of espresso, the answer would be 0.01 molar. Then this question is related to the question. So how many caffeine molecules are in 1 ounce of espresso? So let's start this once again from the front, from the very beginning, and let's think about what's going on. Whenever we are asked the question, how many molecules are in an ounce of espresso, what that's going to require is thinking about what's called Avogadro's number. So what you see at the bottom down here is Avogadro's number. His number states that 6.022 times 10 to the 23rd representative particles, and I'll put RP, are in any 1 mole. So if you're asked to figure out the number of molecules, you can say that there are 6.022 times 10 to the 23rd, and then representative particles is just the way of saying you can put anything in that place. So 6.022 times 10 to the 23rd molecules in any 1 mole. It doesn't matter what you put in there for representative particles. You could put 6.022 times 10 to the 23rd eggs and 1 mole of eggs. Just notice that whatever's on top, eggs and eggs, needs to be on the bottom. So 1 mole of molecules contains 6.022 times 10 to the 23rd molecules. You can also write it in reverse. So you can say 1 mole of people would be equivalent to 6.022 times 10 to the 23rd people. So you can really go back and forth with this. The world population's not quite there yet. I don't think it'll ever be there, but this is kind of the way of going back and forth between notation. So notice, we don't need to really refer to people as moles of people because we don't have that many people on Earth. But with molecules, we do have that number of molecules. We have way more than that number of molecules that compose up our universe. Let's see how we're going to use Avogadro's number. So the question is, how many caffeine molecules are in 1 ounce of espresso? Anytime you see molecules, note you can only get there via moles. You can never go straight from grams to molecules. You have to stop in the middle. So it's sort of like if I'm trying to get from here to Kansas City, I would have to go through St. Louis. Unless I wanted to go through the Boot Hill and take about 5 hours longer. So it's kind of like that. If you've got a train that has tracks and it goes through multiple cities, you can't just jump over cities. You have to go through them. So same thing with this. In order to go from grams to molecules, you have to go through moles. You can't just jump over them. So whenever I've got 64 milligrams of caffeine on 1 ounce of espresso, whoa, why did you get angry? So whenever we have 64 milligrams of caffeine in 1 ounce of espresso, notice that we already have the denominator being perfectly fine. We know we've got 64 milligrams in 1 ounce of espresso, so we don't need to change the denominator. The denominator's fine. It's the numerator that's going to be changed. So like I said, we can't go straight to molecules, so we must go through moles. So from the previous slide, what did we have to do? How did we get to moles? That's right. First off, we converted from milligrams to grams. Then we went and we said, how many grams are in 1 mole? 194.19 grams of caffeine in any 1 mole. And that gives us our answer that we got before. So if we go back here, we got 3.2957 times 10 to the minus 4th moles. 3.2957 times 10 to the minus 4 moles of caffeine. I'm going to go back, just double check, make sure that's what it was. 3.2957. 3.2957 times 10 to the minus 4 moles of caffeine per 1 ounce of espresso. So we've got it in moles. Now we need to get to molecules. So in order to do that, we use Avogadro's number. Avogadro's number always lets you convert from moles to molecules. So in any 1 mole of caffeine, there should be 6.022 times 10 to the 23rd molecules of caffeine. So now you go to your calculator and you type in 3.2957 times 10 to the minus 4 times 6.022 times 10 to the 23rd, and that gives us a total of 1.98 times 10 to the 20th, and that is molecules of caffeine in 1 ounce espresso. If you were to put in the correct sig figs, once again, it would actually just be 1 sig fig. So with this, you really need to make sure you understand 2 things. So this conversion factor here, what is that called again? Our molecular weight. So you use the molecular weight to get from grams of a substance to moles of a substance. Or you can use it to get from moles of a substance to grams of a substance. Once you have it in moles, then you can use this conversion factor, Avogadro's number. And that number lets you go from moles to molecules. You can also go from moles to atoms, or you can go atoms to moles, or you can go molecules to moles. So these are the two big, huge concepts to think about today. Can you use molecular weight as a conversion factor? Can you use Avogadro's number as a conversion factor? If you can, then you're understanding this lesson. So let's do another example. Sorry, I forgot. Before we do another example, though, this is a flow chart that I made that I think might help get these ideas into your head. So the idea here is if we've got grams of an atom or a compound, you can convert to moles of an atom or compound, which is what essentially I just said. But if this flow chart helps you compartmentalize your thoughts, please use it. So with here, you can go from moles of an atom or a compound to the number of molecules or atoms. So if you've got 5 moles of carbon, multiply 5 times 6.022 times 10 to the 23rd to get the number of atoms of carbon. Or if you've got molecules of caffeine, you can go to moles of caffeine, and vice versa. So we've got molar mass, and we've got Avogadro's number. If I were to put these into little brackets to illustrate what conversion factors you're using, if you go from grams to moles, that means you want to end up with moles on top, and your grams are going to be on bottom because they're grams over here that you started with. Then to go from moles to molecules, your 1 mole will be on bottom and your 6.022 times 10 to the 23rd will be on top. And that can be either molecules or atoms, depending on what you started with. Okay. Then you go back the other direction. So now you're starting with molecules. How do you get to moles? Well, if molecules is on top, it needs to be on bottom to go the opposite direction. And 1 mole. Then to go the other direction from moles to grams, moles can be then on bottom to make it cancel, and this will be the number of grams on top. And so once again, this number of grams, this comes from your periodic table. It's your molecular weight. Whereas this one is Avogadro's number. So get familiar with going back and forth, back and forth, back and forth. Just whichever one you need, you can utilize to help get you to the end game. We've got sugar. And I like to put 1 cup of sugar into 2 quarts of sweet tea. So for every 2 quarts of sweet tea I make, I normally put 1 cup of sugar into it. So in answering the question then, we want to figure out what the molarity of my sugar is. Because the sweeter it is, the higher the molarity, the lower the molarity, the less sweet it is. So if we wanted to figure out what the molarity of sugar is based on the way I make it, I would follow through a bunch of calculations. So to begin with, we have to start by asking the question, what is the molecular weight of glucose? So how do we figure that out again? Let's look at it. So once again, we've got carbon. We've got its molecular weight. So 12.011 grams per mole of carbon times our 6 moles. Remember how we did that? So we've got 6 moles of carbon. If you understand how to do it and you want to pause this video right now, I do recommend you do it. Figure out what the molecular weight of glucose is on your own. If not, you can keep on watching. Or you could pause it and then keep on watching. That's probably what I would recommend doing. So, to begin with, 12.011 times 6 equals 72.066 grams coming from carbon. If you notice, our moles canceled, leaving us with just grams. So hydrogen now, 1.0079 grams of hydrogen per mole. We have 12 moles of hydrogen. That gives us a total of 1.0079 times 12, 12.0948 grams of hydrogen. And for oxygen, we have 15.999 grams of oxygen per mole times, and with oxygen, we have 6 times 6 moles of oxygen. So 15.999 times 6 gives us 95.994 grams coming from oxygen. So now we need to add up all our individual components because we have 6 moles of carbon plus 12 moles of hydrogen plus 6 moles of oxygen to give us the total molecular weight of glucose. So our molecular weight of our glucose is equal to the sum of all of these individual components. So 95.994 plus 12.0948 plus 72.066, and since 2 of our elements have just 3 decimals, let's round it to 3 decimals. 180.155 grams of glucose per mole of glucose. So that's our molecular weight of glucose. Once we have that, we can use it in order to convert from 1 cup to grams, then from grams to moles, so that way we have moles as our top unit for molarity. So let's use it as an example to determine, we've already figured out its molecular mass, so then what the molarity of sugar is in my sweet tea, and the number of glucose molecules in 300 milliliters of tea. So let's look at the molarity. Down here I have 1 cup of sugar is approximately equal to 300 grams of sugar. And I think I actually looked that up and I meant to write 200 grams of sugar. So let's make that change. Then we've got molarity is moles per liter, and 1 quart is equal to 0.946 liters. So let's start out with, we've got 1 cup of sugar per 2 quarts of tea. We have a mass on top, we have a volume on the bottom. That means we are representing it as a concentration, which is what we want. So we started from there. So the next thing is we need to convert cups to moles. So in order to get there, we can use this equation down at the bottom, where 1 cup of sugar is equal to 200.0 grams of sugar. Then we can go to our molecular weight because we've gotten into grams, and as soon as you get into grams, you can go to moles. So if we look back on our previous page, 180.155 grams. 180.155 grams of sugar for every, excuse me, 1 mole of sugar. So let's look at our units, how we're doing so far. We've got 1 cup on top, canceling with 1 cup on bottom. Gram on bottom, canceling with gram on top. We're left with moles on top, which is what we want. Now our bottom part, we're almost there for the bottom part. We've got 2 quarts on the bottom. So for every 1 quart of tea, that's equal to, down here, our conversion factor, 0.946 liters of tea. So now we're doing good because not only do we have moles on top, but we can also cancel our quarts, which leaves us with liters on bottom, which is what we want. Make sure we type this all into our calculator appropriately. So make sure you do in fact use parentheses or correct order of operations in order to solve. So we've got 200 divided by 2. Divide that by 180.155. Divide that by 0.946. And you get a total of, and let's do, I was really ambiguous with my sig figs, so we're not going to worry about them for this problem. 0.587, and the units on that, moles of sugar per 1 liter of tea, which is the same thing as saying 0.587 molar sugar. So if you were to ask the question, what is the concentration of sugar in my tea? It is 0.587 molar. What's important about this is typically the way chemicals are given in industry and anything that chemists have created basically. They'll use molarity. Sometimes they'll also use grams per mil, but majority of the stuff will be given as a molar amount. So once we have that, we can then look at answering this question. How many glucose molecules are in 300 milliliters of my tea? So we're going to do a little something different. We're going to start out with the molarity. So if we start out with our molarity, 0.0587 moles, molarity of sugar. Remember, that equals 0.587 moles of sugar per liter of tea. So if we start with that as our starting part, we then can figure out per 300 milliliters. So if we have 0.587 moles of sugar in my tea, then I can say, oh, well, 0.300 is the same thing as 0.300 liters. So I can multiply these to get rid of it, because I don't want 1 liter. I want 0.300 liters. And that's going to tell me how many moles I've got. Because if I don't have 1 liter, if I just multiply it by what I'm trying to get, these will cancel out. Liters and liters, leaving me with the number of moles that are present and only the sample size that I was interested in. So we've got 0.587 times 0.3 is going to give us a total of 0.1761 moles of sugar. And what's my size on that? In 300 milliliters. So we're done. Almost. We asked for molecules. So now I need to convert from molecules to moles. So I have 0.1761 moles of sugar. Now, how do I get from moles to molecules again? 1 mole of sugar is equal to 6.022 times 10 to the 23rd molecules of sugar. So using that conversion factor, I can get us from moles and an amount to molecules. So times 6.022 times 10 to the 23rd will give us 1.06 times 10 to the 23rd molecules of sugar in 300 milliliters of tea. It is important to note that we have done the same types of conversions. So we've used Avogadro's number. We had to use our molecular weight to get to molarity. And then this top line is simply thinking about what's going on. So what does it literally mean when we have 0.587 moles per liter? If you think about it, is 0.3 less or greater than a liter? It's less than a liter. So if we have less than a liter, we should end up with a number over here of 0.1761 that is less than the 0.587, and it's approximately a third less. And if you multiply those across, you see that's exactly what we got. So not only do we do those steps correctly, but our final answer makes sense. So notice, a lot of sugar molecules are in my tea. Have you ever thought about that? Whenever you put just, a cup of sugar into 2 quarts, think about how many molecules you just dumped into that thing. A lot. So think about scale and how it compares whenever you're thinking about concentration. So to recap from today, moles are used to convert from mass to molecules. You cannot go directly from mass to molecules. You cannot go directly from molecules to mass. If you learn anything from this lesson, make sure it's that, and know how to get from one to the other. What do you use to convert from mass to moles? Molecular weight. What do you use to convert from moles to molecules? Avogadro's number. Practice that over and over again until it is like clockwork and you can do it instinctively. Those are the important parts of today's lesson, without a doubt. Additionally, what is Avogadro's number? 6.022 times 10 to the 23rd. And you can use it as representative particles. So any mole of any substance should have 6.022 times 10 to the 23rd of that substance in it. Additionally, molarity is a way of expressing concentration, specifically where you're representing the mass in moles and you're representing the volume in liters. Then the molecular weight allows the conversion of mass to moles, which can be directly compared. And so that's what's going to be really important as we move on, is that you can directly compare moles, but you can't necessarily directly compare mass. So keep in mind that's kind of where all this is building up to. But we have to remember that first bullet point. First and foremost, moles can convert mass to molecules. They're the key to this. They're the key to molarity too, moles per liter.